Okay. Okay, super. Now I realize we can't hear Peter though. Not on the stream. Yeah. Okay. So, good morning, YouTube. Sorry, I've had a really difficult technical mishap with OBS here this morning. Everything is not configured the way I wanted. Um, so yeah, I'm on a call with Peter. We're trying to get this set up. As soon as we've got Peter's voice coming through, then we'll proceed on with the stream. So we need to capture the desktop source, you say. Let me think about this. We could add meet as a hidden video and maybe capture the audio from that. Unless there's an easier way. Yeah, our call directly. Let's just go with that for now.
Audio do anything with?
Let's just go with that for now.
Can you see the volume meter? Audio do anything with?
Let's just go with that for now.
Can you see the volume meter? I'm sure the next string will be perfect from the start.
Let's just go with that for now.
Can you see the volume meter? So I'm guessing we're not there, right?
I'm not sure.
All right, should I?
Are you able to go onto the stream and listen? I think I'm going to get a feedback loop now if I start sharing my audio through.
Oh, I can hear myself on the stream.
I think you might be much louder than me. Is that right?
Well, yes, yes, I'm about, yes, I'm a bit louder. Not too much, but I'm a bit louder, yeah.
Okay, I've turned you down.
Yeah.
We'll see how that goes. Well, I think given we've just had some technical frustrations, let's just get going for now.
I don't know how the syncing will go, but hopefully this will be good.
I think it should be all right because the audio is being captured from our call, so I think the stream should have the audio synced up the same way that we're hearing it, and then hopefully that's all going to work. Right. Well, good. Yeah. Good morning again, YouTube. We've had a bit of a technical mishap. Hopefully, so I'm here with Petr Viktorin from CPython, Fedora. Peter, do you want to introduce yourself?
Hello, I'm Peter. Yeah, it's just CPython now. I work as a coder in residence for the Python Software Foundation, doing lots of stuff all over, but my area is the CAPI. and hopefully making it better for things like Pio 3.
Hmm. Yeah, and yeah, absolutely. Because working on Pio 3 to get the Rust and Python interop between all working well, we obviously have spoken quite a lot in over the years now to do various pieces there. And uh, so the idea here is that we're going to stream together to make some progress on some of the particularly interesting pieces that kind of need like, input from both the Rust side and the CPython side to figure out um, what's going on. And I guess also particularly I'm interested in helping out contribute to CPython a bit more, where there's like things that Rust could really benefit from. Like why rather than just like shouting about it, saying, "Hey, I want this," what if we work on it directly? So the idea is that Peter and I are going to be trying out the stream to work about monthly. Hopefully next month there will be far fewer technical issues getting set up. This is obviously the first time I've been streaming for a little while, so hey, that's how it goes sometimes. Um, and I think the thing that we thought we'd talk about today is about CPython's Unicode objects and how they interact with, well, the data that we would exchange with them from Rust. Um, and there's some particular like interesting things that we could do with Unicode objects. That's not necessarily saying that CPython will do these things with Unicode objects, but the idea of these streams is to kind of give it a go and try, right?
Right. Yeah. Well, that's a question I wanted to ask
Hmm.
before the stream, but let's do it live.
Okay.
So, should this be more about like exploring how the internals work,
Hmm.
and then we kind of get our homework and try to implement things off the stream, or should this be really about doing the change and uh, getting the fastest way you can get to a pull request that fixes something?
Um, that's a great question. I think, well, depending on what particular things we try to tackle, I suspect that this might end up being like a multi-stream effort for some of these, or even stuff that might be, I don't know, some of it might be pep worthy depending on the complexity or what we're trying.
Sure.
Um, so I guess we can just like feel our way through as we talk about things, and like if we find something obvious that we can PR and pull off and merge, then we can do that. I think with regards to like on stream, off stream, probably we will do most of the work on stream for now, but if it makes sense to like continue it off stream because there's like a lot going on, then we can obviously do that as well. And then we can just make the stream. I mean, we could either make the streams more regular or so that people can see that work, or we can just catch up and like summarize what happened just from stream to stream as we go. I guess both are options.
Sounds good. Well, I hope to get some inspiration for between the streams at least,
Yeah,
and I hope
absolutely.
I get the time to implement something.
Hmm. Yeah.
All right
Uh,
then. So, what is the goal?
the goal.
Or
So
the goal? What is the direction we're going? Where are we headed?
so if I'd had my nice handy development setup all ready for us rather than these technical issues I started with this morning, then I would have been able to have a nice like demonstration for you of what's going on and what would be useful. But um, maybe we can start by talking about the nature of Rust Unicode objects or Rust strings and CPython Unicode objects and kind of dig around like the interesting bits between those. We could even try running a benchmark perhaps, if that would be interesting
All
to
right.
play around with that kind of stuff. Right, let's add. So at the moment I've got the CPython checkout, and I can add one more repository, I think. Why don't we add the Pio 3 repository? Um, and then, because I'm more familiar here, so this is easier for me to start with anyway. Um, all right, so we've got a clean Pio 3 main. Oh, all right, right. Now we've got a clean Pio 3 main. So we can have We don't have any good stream benchmarks in Python 3 at the moment, but we can make one, that's fine. Let's just put it here for now. So if we are creating a Rust string, then a Rust string is a Unicode UTF-8 string. So we can actually play with this a little bit here.
So now the text is hidden by the camera.
Is it? Oh yeah. Okay.
Yeah, maybe make the file list bigger.
Yes.
If that's configurable.
Again, on the so I was going to stream on Ubuntu desktop, but I had some last minute issues, and so that's why I'm now streaming on this Mac OS system. But everything is not configured in the way that I normally would have it. So I think we've got the font size on the file picker a bit bigger now. Is that more legible?
Yep, that's more
Okay,
legible.
great.
The problem is the camera is covering the a part of the screen. So
Yeah, I
there's an
think
fn create string, and I don't see what's inside.
there's nothing in there at the moment.
Oh, there's nothing in there.
But yeah, okay. I'll just have to keep code out of that corner of the screen. Ideally, the background for my camera would be transparent, not this black, but that's I couldn't work it out with a Mac OS system, so hey. Sorry about that. Right.
Maybe you can move the picture in OBS.
Just make it smaller. That's probably fine.
Make it smaller, move it partially off screen.
Gunboot. The IDE I'm using is Z. It's
in OBS, the camera feed.
in OBS, the camera, just make it smaller. I can potentially
Move
crop it as well,
to the
actually.
with Alt. Well, I don't know about your keyboard, but there's a modifier you can use to drag the side.
There we are. That's going to work better.
Yeah, nice. All right.
Okay, that's given us a bit more space. Super. So if we want to, okay, so Copilot's actually just gone and thrown in the solution there for us, which we'll do just to show the point. So in Pio 3, we've got this is Rust APIs to go and basically automatically start up an embedded Python interpreter. I'm explaining this for Peter as much as for everybody else watching as well, because I don't think you're super used to how Pio 3 does things.
No, I'm not. So what does this Python attach to?
This is it's heading towards the idea of, hey, now I have an attached thread state, so I can do stuff with the Python interpreter. Is what the attach is called, but we have an option. It's not automatically set, so that if there's no Python interpreter running, it will go and call pyinitialize the C API and start up the Python interpreter for you in the background, so that then you're just ready to go. And for writing Rust tests and benchmarks, this is a really convenient way to just try stuff.
Yeah.
And so once we've got the Python interpreter, then this is a Rust benchmark framework called Criterion. It gives us this iter function, which allows us to go and pass in what we want to do. So it's going to create, you probably want to allocate the string outside of the iteration, to be honest. And then we're going to go create a Python string from that. And we'll dig into like how this actually is working in just a second. I realized that having answered the other chat question, I should probably try and get the chat window up on my screen so that I can see that in case there are any more questions.
Oh, what's the IDE you're using?
Yeah.
Z, right?
Z, yeah. I was a long time VS Code user before I switched to Z. No, I cannot for the life of me find a way to keep that window on the top.
I'll keep it on top.
Okay, thank you. Well, maybe I can see it through this one. Okay, that works. I have a way to see chat now. Yeah, so if we run this thing, we can do in the Py3 repository, we'll just use the UV first of all to run Nox. Nox is a command runner. It's a bit like Tox. It's one of the sort of testing tools. We use it for writing scripts for all the things we want to do in Py3 because it's just a handy way to get it. So we've called this bench. We've added this to bench any, and we just select the string one. This should now run. We'll have to do a Rust compile for a moment. And we can dig into the mechanics of what's going on here maybe while that compile's running. So if I click through
that.
Oh, I've forgotten to add the benchmark here. That would be a smart thing to do. Okay, so now we're just running the benchmark. Okay, so here we are. And we've just, I mean, it's not particularly interesting. It ran it, it worked out for this particular arbitrary string that it took 65 nanoseconds to create the string. But I think what's more interesting is talking about how this is working and what we could potentially do here to like avoid inefficiencies. I think this might be a good way to prompt discussion, Peter, on what we might want to try when it comes to upstreaming various things.
Sure. So PyString new, I guess, does Unicode new then.
Yes, so let's hide the terminal for a moment and look at the new function here for the PyString new. So we have a Rust UTF-8 string, some text.
So a Rust UTF-8 string, so that's a bunch of bytes, right? It has an attached size?
Yes, so Rust has two string types specifically, which are most relevant for us here. So we could have the string slice, we call it, which is, we can create it as a string literal like this. And it is we call it in Rust nomenclature, a fat pointer. So it contains both a pointer and a length.
Mm-hmm.
So it's not a null terminated string. It is, in this case, it would be pointing into static storage for the text A, B, C, D, and it would say it was 4 bytes in width.
Right.
You can also have
UTF-8, and it's guaranteed to be UTF-8.
Yes.
UTF-8.
Yes. So the Rust stir and string types are definitely UTF-8. That's an invariant. So we can also have an own string. And the difference here is that for the own string, it's actually then got an allocation on the heap for that data that's owned by the string struct. So you can move this about your program. When you finally dispose of the string struct, you're also deallocating from the heap.
Right.
But again,
so the string slice just points into some memory that the compiler knows it will be there while the slice is alive, right?
Yes, exactly.
And the to owned that's managing its own memory.
Yeah, we've got a heap allocation going on in there.
Nice.
And so we could actually have borrowing the data back out from the own string. So now this would again be a stir reference like this. Technically, there's what Rust calls a dereferencing operation going on here. Like the naive thing, you think this would be referenced to string, which is more true, but then you can do a dereferencing operation implicitly to cast it to the slice form as well.
Right.
So the interesting thing here is that we have in this PyString new method that we're looking at this argument that is a string slice where we know that it's UTF-8 data and it's got, yeah, a pointer and a length. And CPython has an API that works near perfectly from this, right? Called PyUnicode from string and size, where we give those
Yep.
two components a pointer and a length. And the interesting things to talk about here are what's going on behind the hood in PyUnicode from string and size. And I guess this is where
So
we can.
PyUnicode. So CPython API was not renamed in the Python 2 to 3 transition.
Mm.
So here all the strings are called PyUnicode. So that's why the name. And the from string and size, that means from C string and size.
Yes. So here's the API
so UTF
in
encoded bytes and a size. So this is a C style fat pointer. Where it's not a fat pointer at all, just a pointer and an attached size.
Unfortunately, CPython actually even has in the header here, it expects it also to be a UTF-8 encoded string. So
right. So that's you're using this function, which expects a UTF-8 encoded string. There are other functions to create a string that are more close to what's stored under the hood.
Yes.
But yeah, this one expects a UTF encoded, not necessarily null terminated string and size.
Yeah, absolutely. And so the interesting thing then is what's going on behind the hood in this function, I guess, because ultimately that's the price that we're paying every time we call this API. So we can go in and maybe talk about the Unicode internals a little bit, which we've had to deal with before in Py03. They're not, I actually don't know on CPython main how public they are anymore. Let's try.
CPython on Unicode object.h.
Yeah, and I think, so here we should find somewhere the struct. Okay, this is the state, which is even more complicated than it used to be. Here's a struct, which is, okay. Maybe we'll start here. So we found the struct PyUnicode object, which contains a PyCompact Unicode object, which we'll talk about in a moment, and a union of the data, which is a pointer to where the data is actually stored, right?
Right.
And this is now reaching into CPython internals, and so you're going to have to correct me if I start feeling like I'm wrong on any of these points. My understanding is that we have CPython stores data in 3 possible formats, none of which are UTF-8.
Yes. So so Python historically in Python 2 strings were just bytes. Then this newfangled Unicode object came in and it stored Unicode, and it behaved just like the old byte strings, except on Unicode characters, right?
Yeah.
And UTF-8 wasn't really that popular back then, I think. So
yeah, makes sense.
Well, the important thing here is O1 indexing, right? So if you have a Python string, you can ask for character number 158, and it'll give you that character instantly.
Yeah, absolutely.
And this is why we cannot use UTF-8 easily to store Python strings, because if you have UTF-8, the Unicode characters take up different amounts of space. So to get a particular Unicode code point from Unicode string, and it's in a UTF-8, you would have to go through the entire string and count.
Yeah.
Right. Or use a more complicated indexing data structure, which Mark Shannon would be happy to implement, I'm pretty sure.
Yes.
But yeah, so this was the time when Python was prized for its implementation simplicity, right? So this is where we are.
Yeah.
So the most naive way to do this would be UCS4. So you can put any Unicode character in 4 bytes.
Yeah.
So just have an array of 4 bytes, 4-byte characters. That would be your string. This is very wasteful if you just have ASCII data. So if we just have or Latin 1 data, everything fits in 1 byte, then we have an array of 1-byte characters. If everything fits in 2 bytes, which is well, at the time that was everything, we have UCS2.
Yeah.
And if you throw an emoji in there, you have to have 4 bytes per character.
Yeah. I guess. I mean, and this is a good strategy, right? Because it's very memory efficient, and you get the O1 indexing that you talk about. So
yes.
when I guess the example that I've put in the terminal here on the side, this is an ASCII string now. So that means that under the hood, the data is going to be stored as a UCS1 format, so 1 byte per character. And in fact, there's probably more things going on there than just this naive representation, because we've got this PyCompact Unicode object. So maybe there's even more.
That's the metadata.
Okay, so
yeah.
we always have a full PyUnicode object, do we?
You don't. So if you go up, there's a PyCompact Unicode object, which has a PyASCII object.
Yep.
Right? So let's start out the PyASCII object, which is giant comment, and then
yeah. Oh right, yeah. This is all. So this is the content.
So there's PyObject head. The PyObject head historically is the ref count and the type.
Yep.
Now it's a bit more in free threading, but that's basically all Python objects need this.
Yep.
Then we have the length, which is the size of the string in Unicode characters.
So for our toy string, it will be 7. For example.
If you do len, it looks up this number and gives it to you.
Mm-hmm.
Then we have the hash, which is -1 until the string is hashed, and then it's set to the hash.
Yep.
So you don't need to hash the string again.
Out of curiosity, does that mean that a hash value of -1 is totally impossible?
Yes.
What happens if the string ever collided with the hash of -1 by chance?
So the internal function that returns the hash treats -1 as error.
Okay.
So every object that does hashing has a little if at the end. If it turns out to be -1, return -2 instead.
Oh, interesting. I wonder.
You can actually hash. So for integers hash to themselves if they're small enough.
Yes.
For simplicity and for explaining this. So if you hash an integer in Python, you get the same number back unless it's really big. If you hash -1, you get -2.
Oh, interesting. Okay. So that means if we do hash -1 right here, we'll see that. So that means that you have a hash collision trivially. I mean, it's not a very scary hash collision between these two straight up. I suspect that, I don't know. So you're saying that is handled in each object's implementation, not in the interpreter. Yes. So, but it makes sense, right? Because if the hash function is returning -1, the interpreter has to believe that is how error reporting is done through the Python C API by returning -1.
So that is how error reporting should be done. And as a member of the C API working group, we're only adding APIs. Well, only adding APIs that do this. So there is a return value that is reserved for the error case.
Yeah.
Right, and that's -1 in this case. There are some old APIs where a -1 would be ambiguous. So either was an error or not, but those are old. We don't do those anymore. So for hashing, -1 signals an error.
Yeah, I have a feeling
and that's because
that Pyo3 doesn't guard against that. I suspect that if by chance a Rust object hashed to -1, it would probably cause a system error by trying to fetch an exception that's not there. But that's a problem for another day.
Oh, well, -1 is an error. You can always check if an error happened by calling pyerror occurred.
Yeah.
So that's kind of redundant.
we can explore that maybe in a moment. That can always be a patch
So,
for
well,
player three.
there's the hash. And also, if the hash value of a string is -1, you know that it hasn't been hashed yet.
Yeah, yeah,
So,
because it is caching it effectively, so that next time you call the hash, it's much faster.
right. So don't go poking there, by the way, manually, because you need atomic rights nowadays to set the hash.
Yeah.
So there are some helper macros to do that.
Hmm.
Anyway, next up is the state. And this is aligned for optimization reasons. So it's always aligned on a 4-byte boundary.
Hmm.
And it's a struct because of weird C and C++ intersection syntax. So it needs to be a separately defined struct that's a bit above.
Yeah.
So this used to be a struct like right in like defined right on here, but that doesn't work with all the ways you need to do to get all the C compilers to align things. So now it's just been moved outside, and it's this by Unicode object state, which you can see just above this definition.
I'm okay. That's interesting. So you've specified the alignment on the field rather than on the struct. Is that a C specific thing? Because I think in
That's
Rust you
this.
would do it the other way around, and you would say, "Hey, this struct wants to be 4-byte aligned."
Yeah. So this is a public header,
Yeah.
which needs to be compatible with C,
Yeah.
and ideally rather old C, and also C++.
Yeah.
So there are all kinds of quirks that that go into this,
Yeah.
and this is one of the minor ones. So this struct tells you everything you need to know about how the object is stored internally.
Yes.
So there's a bit more complication for free threading is the intern state, which needs to be accessed atomically. So it's its own byte, even though it only needs 2 bits.
Because you need to do atomic reads and writes to it.
This also, so yeah, there's a comment above. So
Yeah.
0 means it's not interned, 1 it's interned, 2 is interned and mortal, 3 interned, immortal, and static. So all 4
Mm.
options are taken now, and for ABI compatibility, which is not guaranteed, but some projects need it in the non-free threaded build. This is a bit field, so it's just 2 bits, and the rest of this like integer sized thing are taken by other bits.
Yeah.
And the other bits
Yeah,
are
we've got.
down here.
And when we talk about ABI compatibility, what we mean is that because this is in a header, there are actually some of these methods to interact with Unicode objects in the Python C API are touching these bit field components, right? And so then it's effectively baked into the well, the ABI, as you say. So it's not possible to change these without breaking things.
Right. So there are 3 bits for the kind if you go there. So
Mhm.
that this can be 1 for UCS1, 2 for UCS2, and 4 for UCS4. So 3 variants, and we need 3 bits because we want the number to correspond to the size of the field. So we kind of waste a bit here for optimization, I guess, or simplicity.
I guess it gives you space to potentially add more kinds in the future, or
It does, but if we added something new here, that would also break the ABI, so we would be free to add another bit to this. But
right,
that's not the reason.
which you could do across minor or major Python releases anyway.
Uh,
Um,
so by policy, by documented policy, we could, but it would anger some people. So we'd rather not if we can help
Understandable.
it.
Hmm. Yeah,
Uh, so my goal is to remove this from the API.
yeah.
So this would be a pick, and you would always have to go through functions or through macros to poke at the bits. So we would be free to change this around. And one of the things we could do then is add actual strings that are backed by UTF-8 strings.
Yes. So this would
So
it would be a longer term
yeah, I guess
project.
the long-term goal here is to add a new kind that's UTF-8.
And to give an example of what you mean by that as functions, so there are two ways to get the Unicode kind value from these Unicode objects in the API. So there is the PyUnicode kind function, which is available on more recent CPython versions, and this just takes an object pointer and returns that kind as an integer, and the implementation of it is completely opaque. That's internal to the interpreter. You call this as an external symbol, or for older implementations, or indeed, I don't know why this is defined right over the top here.
Yes, that's
It means
so.
that this is never called if you're using the.
This means that if you are not using this header directly, if you're Pyo3, in other words,
Yes.
then you have the function to call. Or if you're using C types from Python, right? There is a function that you can load the normal way from your DLL and call it.
Yes.
Right?
Okay.
But if you're using the headers, there is no DLL loading and calling a function, and because that is not free, right? So
yeah.
If you're using the header directly, it means you're not using the stable ABI because this is like a CPython only header.
Yep.
Then you get this implementation. You just plug the value out.
Mm-hmm.
And this is subject to change whenever the internal ABI changes. Whenever the CPython API changes. So for a new major version, this could be different.
And by different, you mean we might remove this, or just that?
Well, we might make it do something else. A good example is getting the intern state. If you can get the function to get that, I forget what it's called, but maybe it's a bit up there. I just look for intern. Yeah, that's the one. So check intern. So
yeah.
It used to be a Boolean, so it was a check. Now it's 2 bits, right? So this is actually different between the GIL build and the free-threaded build and the GIL build, right? There's an atomic load for free-threaded, and the faster normal load for the older, for the GIL builds, right? So this is a change we can do in a new major version, right? We can change the implementation to do something else.
Yeah.
And that's why you should always use the macros or the functions and not poke in the struct directly, because we can always add something like, now you need an atomic load.
Yes.
Or shuffle the bytes around.
I guess if this struct were defined today, would it have an underscore on it, which I understand is kind of the, hey, don't touch this, but it's here for ABI reasons sort of nomenclature. Or indeed, you might not have this in the header at all, right?
Right. Oh. Is it?
No, I just added the underscore there.
Oh, you added it.
Yeah, sorry, that's confused you. I was just added it for demonstration.
Yes, if this was added now, we wouldn't put it in the header. Or we would add the underscore because the macros need to see the definitions, but you end user or like users of the API should never touch this. So if you go up again, so there's the state one more up. In the state we went through kind. There's the compact bit. There's the ASCII bit, which also affect the representation. And then there's the statically allocated bit, which is for strings that are hard-coded into CPython and are accessed a bit differently. That doesn't really concern us because you cannot make those through the API.
Yep.
And there's a bit of padding because C reasons, and that's it. So we have kind, compact, and ASCII. So this is the state, or like the description of the state and the representation of the object. So if you go down to the PyASCII object struct, you'll see that this is the final field, and you might be asking yourself, where is the data?
Ooh,
Right.
let's. So I think I can guess at that if you'll let me try.
Sure.
So when allocating a PyObject, there are two categories of PyObject that, in sort of a broad sense, there's ones that are PyObject of a fixed size, and then there are PyObject which can also have a variable size allocation that are called PyVar object. And if I'm going to guess at what's going on here, the idea with PyVar object is that they have an item size, and when allocating a PyVar object, you say, I know that I need space to allocate for 8 items or whatever, and that space is allocated directly after the object in memory. So if you index past this PyASCII object state, then if my guess is correct, we could say, I need an 8-byte ASCII object string. We'll allocate space for 8 bytes at the end. You can index past that to get to the data.
Right. So yes, so PyVar object is the pretty sane variant of of all this. Like, so that's what you should use for objects that can have different size when you allocate them. So a tuple, for example, would use this because it has a fixed per instance size.
Yeah.
That differs between the instances. Right, the list of pointers is directly in the allocation. PyList doesn't use this because that needs to grow.
The allocation
so
can change.
To reallocate the internal array.
Yeah.
So if there's a fixed per instance size, you would use this. PyUnicode is a bit different. It doesn't actually use the PyVar object, but internally it's pretty much the same. So it has a length inside it. Yeah, it's not a PyVar object because historical reasons.
Okay.
You can cast it to a PyVar object, and it works. You just get undefined behavior in C, but that's fine because it works on all platforms. Don't do that.
Let's not. Yeah.
So yeah. You can. So the length is just after the head. That's how a PyVar object works. Right?
Yeah.
C doesn't define that it works, but it does.
Because a PyVar object is actually, oh no, I've gone into Rust code there. Never mind. I haven't got the indexing working on the CPython repository.
PyVar object is just PyObject head and PySize T. I don't know what it's called, but it's the length.
Yeah.
Right. So if you call the CPy function PySize on a Unicode string, that's undefined behavior per C, but it works.
Good to know. Okay.
Yeah, you should always use the PyUnicode size or something like that, which does the same thing internally. Anyway, so yes, so this describes the header, and for simple Unicode objects, the data follows just after that. So this is called PyASCII object because this is the representation of ASCII strings.
Yeah.
And it's Unicode so some ASCII strings. So if you create an ASCII string the right way, it will get this extremely compact representation. It'll get the ASCII bits set in the header, and the data will follow just after this header. So that's the minimal header you can have for a string object. There is one thing that's not so nice, and that is this ASCII string has a null terminator at the end.
Oh,
So
okay.
Python strings are guaranteed to have a null at the end, even though they can internally include nulls and they have a length. For interop with C, there's the guarantee that past this buffer that is important to you, there's a null, so you can safely call C functions on it. And of course, people
Hmm.
rely on it.
Yes. Okay, that's interesting. That that will make interesting interacting with Rust a bit
Yes,
more interesting.
that's the reason I'm saying that. Foreshadowing. I think
Yeah.
I haven't written the script, but yeah, I think this is a foreshadowing. Uh, yeah. So if you go down to the PyCompact Unicode object,
Yep.
so these are objects that you have created the right way through the right APIs to get the most compact representation you can, but they're not ASCII. What does not ASCII mean? Not ASCII means that the UTF-8 representation is different from the internal representations, which is 1 byte per character, right? So
Uh, okay. I'm
UTF-8 has the property that if you only have ASCII characters, it's the same as the ASCII representation.
yes.
Yes, so this is different. This is the difference between Latin 1 and ASCII.
Hmm.
ASCII is 0 to 127. So the first half of the space of the byte,
Hmm.
and Latin 1 is just 1 byte per character, but it can include the Unicode characters 128 through 255, right?
Okay.
So the ASCII string only has this one ASCII buffer, which is also UTF-8. PyCompact Unicode object has everything. I think you deleted something on line 167.
Oh, yeah,
Yeah.
sorry.
So it has the base, so that's everything that the ASCII object has. And then it has UTF-8 length
Hmm.
and a UTF-8 buffer. And the fun thing about these is these are filled on demand, right? So when you create the object, these can be null. When you
Yeah.
ask for them, they're filled from the string data.
Yeah. And so the string data in a PyCompact Unicode object is still allocated just past the object
Yes.
in the same way. I'm still not.
So if you have the compact bit set in the header, then this is the struct used for the string, and the data follows this header directly. So it's not at the same offset as PyASCII object.
Yeah.
It's after the length and UTF-8.
And so this would be used for the Latin 1 encoding, is what you're saying.
No, this would be used for all the encoding. So this is all you need. This can encode all the objects.
Um, well, hang on, but depending on your, sorry, but for one
So
byte per
okay, so
string,
so if you use the correct new Python API to create a Unicode string,
hmm
you will either get a PyASCII object or
hmm
you will get this compact object, right? And
yeah,
there's one more struct for backwards compatibility, which is a bit bigger and less efficient, right? But PyCompact Unicode object is what everybody should like is enough, right?
okay,
The next one is for backwards compatibility only.
so that's a full PyUnicode object,
Yes.
and that has the,
And that has pointers to data that could be allocated somewhere else that doesn't have to follow the Unicode directly, but that could be allocated somewhere else.
mhm. And so you're saying that in this Latin 1 variant, then this typically is not hit because the PyCompact Unicode object is good enough to represent the Latin 1 encoding.
Right. So in PyCompact Unicode object, the data follows the header directly.
Yeah.
In PyUnicode object, you have a pointer after the header,
Yeah.
and that points to somewhere else.
Yeah.
And that data is allocated separately, and it's still owned by the string object. So it'll be deallocated when the string object is.
Mhm.
It just lives somewhere else, so it's less efficient. But for backwards compatibility reasons, we still have this.
Yes. So should
And,
we?
and backwards compatibility reasons being this is public API. It's in this header, so you can use it.
Yeah. So that you're saying that in a new API there might not be this variant because PyCompact Unicode object could represent it anyway, and that
No,
you still need.
so no. In a new API, we wouldn't have this at all.
Um, you mean the
You
whole
can put
structure? Yeah.
UCS4 data or UCS2 data in PyCompact Unicode object. The
Don't you
data
need to? Oh, because you know the
the
kind.
data
Sorry.
follows. The data follows the header.
Right.
That's
Yes.
the only
Sorry.
difference.
Because the kind is already stored in the ASCII object state. So
Yes.
PyCompact. The only difference between PyCompact Unicode object and PyUnicode object is the allocation is external. I follow
Yes.
what you're saying now. So
Instead of the dark data, there's a pointer to it. Yeah.
so this could be 1 byte per character, could be 2 bytes per character, could be 3 bytes per character, but the data is immediately after the structure in the single allocation. In this, you've got two
Yes.
allocations, so it's somewhat inefficient.
Yes.
So,
So the
mhm,
moment this disappears from the public API, we get rid of this struct entirely.
okay, and then you've already saved some simplifications, which is a step towards cleaning things up and making the interpreter simpler, right?
Yes, but
Okay.
so the problem here is there is currently well the problem I forgot, it's been so long since I thought about this last, and I wanted to get in 350 get it in 315. That's too late. Yeah, so there is one problem about deprecating this PyUnicode object that I could dig up for next time if we want to go there. But there is a problem with deprecating it. There is a use case that is not served by the current C API and will be a pain to fix. So the fix is adding new APIs you can use uh, to enable this use case, which is creating custom subclass. Oh, it's in
Yeah,
the comments.
I
Yeah,
was
custom
gonna say,
subclasses of Unicode objects, which add additional data after this header.
yeah,
That's it. Yes. So if you're wrapping a Java string, you want the pointer to the original Java object in your Python object so that you can release ownership of it. Like the Python string needs to own the Java string to make sure it stays alive.
okay.
And so you need a pointer to the Java object from your Python object. But if the data follows the header directly, you can't really put it there because that
Or
would be overwritten with the data. So that's why we have the pointer, which is a fixed size, so you can put the Java pointer after this. And I think we just lost all of our listeners now, didn't we?
um, uh, I see.
Yeah, I need
Right.
to write a PEP about this, which means explaining it in a way that you can follow. But yeah, there's the use case for Unicode subclasses
Mhm.
where we need to do something about them to get rid of this mess.
It's interesting though, because that sounds like that could be a way that we want to talk about interacting with Rust objects in the same way, rather than having to do too much to CPython itself to support them. So, this might actually be relevant to us as well in what we're talking about here, rather than just for Java strings. I guess we've still got the null byte at the end problem, but we can think about that. Um, so okay, but yes, I guess the other alternative is rather than having this pointer, you could still have the data in the allocation, but have some abstraction that means that when indexing, it's not past whatever the PyContact Unicode object is, but the actual size of the subclass. It much which presumably gets a lot more complicated, and even worse, you then have to copy all the data into the allocation. Maybe with this way, the Java string can just be referenced, so you don't need to copy. I guess maybe not because the formats are probably not going to match Java exactly. But yeah. Anyway,
Um,
that's getting more complicated than we need to right now. Shall we
it
jump
is a bit.
over and just look at the implementation of a PyUnicode from string and size? So going back to
So there's one difference that will probably be important later,
mhm,
in addition to the null byte at the end, and that's Python strings do not have to be valid Unicode. They can
yes,
contain lone circuits, and they can contain uh, code points that are too high. Right?
yes,
So in the 4 byte space, there are some values that are not valid Unicode, and Python string object, or at least CPython strings can just store any number that fits in 4 bytes.
yes.
Uh, what that means is if you ask for a UTF representation of such a string, you get an error.
You can, yeah.
You get a Unicode decode error. Uh, there is a representation, extended UTF-8, that can encode this as something compatible with UTF-8, which is what I would probably use if we're backing strings, like if
Hmm.
we're switching to UTF-8 back strings. Uh, and
Yep.
that also means we can theoretically get rid of the null byte,
Why would that
since
allow
we're
us to
doing
get
a
rid of the null
different
byte?
since we're doing a different format anyway, and we need new API for it. You can just say, with this API, you're not guaranteed a null byte at the end
I see.
if we're adding new things.
Hmm. Okay.
So
Um,
that's like a possibility, a brainworm for the future.
okay. Righto. Shall we look at the implementation of PyUnicode from string and size just to kind of go back to
Yeah,
where we were
let's
looking
do
at
that.
the beginning? So I will find that, I guess, in Unicode object.c, I will expect. Here we are. So we passed in our pointer to our Rust text and the size of that Rust text. And well, first we need to check that some invariants like the size. That makes a ton of sense. Uh, we then why is it this way around? Oh, so then we
So there are two ways you can create Python strings. You can
right.
either give the data up front, or you can create an empty string and fill it up afterwards. And the latter has all kinds of weird behavior because the object is created and Python strings are supposed to be immutable, but now you're filling it up. Uh,
Yes.
so if you, for example, ask the garbage collector for the object it's seeing, it gives you a string that is still being mutated. So we're trying to phase out this API as soon as possible, but of course it's very foundational, and you can't really get rid of it.
Yes.
Uh,
And I think
so
this
yeah,
is going
if
to.
U is null, you get an empty string which you can fill in afterwards.
Mm,
Please don't do that.
yes. And I think that is going to overlap really clearly with what we might play with in the benchmarks in a bit if it's like going on what I had in mind.
Hmm.
So just to show some different code paths that we can currently take, and it might inform what we want to think about next. Okay, let's go find this symbol. For next time, I will have to make sure that I've got the IDE hints working as well. Um, Here we are. So this is the. Oh no, we're still not. Here we are. So we've got the Unicode decode UTF-8 implementation, which is doing the code path where we've actually passed some data, and we're going to let CPython work out what's going on. And here, um, I've peeked at this before, so maybe I can have a go at trying to guess at what some of these things are doing,
Yeah,
because I
so
think,
this is the implementation of the Python bytes dot decode as well. So it takes an error handler and lets you specify what happens if there's invalid UTF-8.
yeah, so that's basically calling, just in my terminal on the side, it would be the equivalent of that, right? We've gone through
Yeah.
this function to achieve this, because the default encode or handler is UTF-8, right?
Yes.
If I can type that. And when you say error handler, I think that is something like this. I might have misremembered.
Yes, that's the
Um,
default.
so if we added um, some, oh, that's worked. I'm not sure
Yeah.
off head how to get an invalid Unicode
Do
character.
FF. Put FF in there.
XFF. Oh yes, of
FF,
course.
yeah.
So now we've hit an invalid
That's
byte. But we can also have, there's like replace one, and it just
right.
replaces it with the invalid character. So all of those code paths are handled by this function.
And there's also like the surrogate paths, I think, which
Yeah,
lets you, which is like the modified UTF-8 that can encode any.
maybe replace. I I know the one you mean. I can't remember exactly how to get to it, but it's going for exactly what you described, right? It puts
We'll probably
um,
see it in the implementation.
yeah, we might well do. So we'll go back to that. But it essentially puts invalid Unicode bytes into the Python string. So then decoding it as UTF-8 later would fail. You can go back through the surrogate handler to go back the other way, right? To recover the original bytes. And this is important for some use cases, which is why it exists. But it adds to the complexity, as you say. Um, okay, size 0, return the empty Unicode singleton. I guess that makes a ton of sense. Um, and that's a nice simple path. And then there is a single character fast path, which I'm going to guess that all of the Latin 1 characters are immortal, and so you get optimizations
Immortal
if you try to
inference, yeah,
decode.
fixed points in memory. Yeah.
So
There's
that
an
would
array of
mean
them.
that's going to mean that if we do this twice, we're going to get the same ID both times, right? Because it's just going
Yes,
to hit the same thing. Whereas maybe if we did it with a longer string, yeah, we're not guaranteed to get the same ID as we see.
guaranteed. Yeah, so this is compiled in. Every build of CPython will give you the let's say one.
So next, after we've done the fast path for 0 and 1, this is presumably checking before we try and actually allocate new buffers that we're not going to overflow uh,
Right.
of some form. It's a comment saying maybe not necessary. Let's not worry too
So
hard about
so
that.
yeah, so there's the size is represented in a pi s size t, which
Hmm.
is signed size.
Yep.
So theoretically, you could request something that's bigger than half the addressable memory space,
Yeah.
and that would overflow and make things negative, and that's pretty bad. Uh, and
Yep.
yeah, so this basically checks that the size for the data minus the plus the size of the header will
Yeah.
fit in uh, whatever space we can represent.
And basically avoiding going into a whole mess of yeah,
Yeah.
oversized allocations and buffer overflows and stuff like that.
Yeah. Nowadays you don't ever have as much memory as you can address, so this is not that important.
Hi, xClary. Yeah, we're looking at Unicode stuff. The questions we want to ask is how fast can we exchange Unicode data between Rust and CPython? And there's obviously a lot of details that we need to talk about before we can even decide whether we're going to do something there. Next, we have this step, which is going to find the first non-ASCII character. So uh, that makes a ton of sense that what we're trying to do is decide whether we want to, having just looked at all of the Unicode representations, can we make an ASCII object directly with all of the upsides of that, or do we need to do more complicated decoding? And so
The find
this,
first on ASCII is heavily optimized.
yes, that's going to be basically ON in the length of the string and fairly efficient. And if we get to that, then we can create just an ASCII string straight up. And we can copy the data in.
So it's ON, but it's also not duplicated work because it finds the first non-ASCII string, and now you know that that part of the string is ASCII, right?
Oh, right. So if you're doing work later, you can at least skip decoding up until that point as well, is why we get the
Yep.
position. That makes sense. If we get the ASCII, we can copy it straight in, which is a great fast path. If not, then we go into
We continue.
Unicode
We now know
decoding.
we have a non-ASCII byte at this location.
Yeah. And so we have to decide what to do about it. And uh, we talked about the error handlers for the surrogates or other invalid bytes like XSFF, and that this is configurable. Looks like. Let me just read this. The error handler of the string may remove, replace the invalid byte.
Yeah. So now it's time to allocate memory for the string. So to allocate memory, you need to know how much memory you need, which means you need to go through the rest of the string and find the highest code point and see if that fits in 1 byte or 2 bytes or 4 bytes.
So how have we got? Okay, yeah. So that's just branching off the exact one that we found that was non-ASCII though, right?
Yeah, it should start there.
Um, oh, I see. Hang on. So it starts there, but it needs to work out.
Needs to work out the max character.
Don't you need to check the whole remaining buffer to decide?
Yes, that UTF-8 code points will do that, I think.
That looks like it sets the max size, but not the.
Yeah, it gives you.
Oh, I see. It says it right here in the comment. We only calculate the number of code points. Don't determine the exact max character because writing fast finds that max character is difficult. Fine. Okay.
Oh,
Right. So we have. So we.
oh, okay. So you
Okay.
use reallocation. Ah, okay.
So the code points are worked out now, um, so that we can make an allocation with PyUnicode new, which is one of the APIs for mutating an in-place one, right? But it's so this will create a buffer that then gets written into.
Yes.
There's lots of decoding going on here. We can. I don't know whether we want to go look at the depth of this even more. We
So I
could.
guess it reallocates if it finds a high enough character.
That would make sense, right? Then it can assume maybe what is currently needed based on the invalid character it hit, allocate a buffer accordingly, and then if the decoding later hits an even bigger character, you can like step up. But you, at worst case, you'll reallocate twice to step up twice in size, rather than
Right.
if you're I get and you because you know the code points. If you don't know the code points, then as you're reallocate, you're going to have to continually reallocate as you decode as well, because you can make uh because I guess you could worst case it, but it's not going to be helpful because you end up with too much memory at the end. So
Right.
it makes
And
sense.
there's also I think there's also a case where you need to reallocate because there's an error in decoding and you need to replace the failed character with something
Yeah.
that's not Latin 1.
Yeah. Okay.
Or you need to replace it with like a hex escape, which is bigger than
Yeah, of
the
course.
size thing.
And then you need to go up as well. Okay. I'm not sure I want to read through the UTF-8 implementation
Yeah,
right now.
yeah. Somebody figured out how to do UTF-8 decoding
Um,
specifically in Python. Yeah, let's not go through that.
I guess the questions that I have that maybe the interesting questions to ask is there's uh, a lot of machinery around the error handler that
Mhm.
and the possibility that decoding may fail. And now from a Rust string, we guarantee that this is known good UTF-8. So there is there shouldn't be a need to have like fallibility on the decoding, and I don't know if
Mhm.
that's going to have a meaningful performance like improvement or not,
I would guess not,
because
because
it's
this is
basically
branching, right? And the branch predictor says everything is fine until you get an error.
yeah.
If you're not getting the errors, then it's fast.
Then you wouldn't expect anything to be an overhead. Yeah, that
Yeah,
makes total sense.
I, I don't think
Uh,
we should measure that.
yeah, absolutely. Um, I mean, other than this looks pretty much as good as it can be, right? The ASCII case is already optimized here, and I mean, there's a check for it being ASCII or not, but I doubt that that's going to change much on the Rust side. Um, and it copies it in. So I'm not entirely sure, other than talking about the UTF-8 representation, where to go from here if we were going to talk about this being easier to interoperate.
Well, so easier to interoperate. Yeah, this is what you do. If you have a string in the Rust representation, which is very different from the CPython one in a
Mm,
way where you always have to have a new allocation, uh, then yeah, we can't. I don't think we can do much other than micro optimized what's already micro optimized by smarter people than we are.
yeah.
Uh, so I think the only way we can make this faster is switch CPython to use Rust's memory representation,
Okay. Which is a
which is
big long
valid
undertaking.
UTF-8 without trailing 0 byte, which is very different.
Yeah. Do you think it's interesting to start uh, hacking on such a representation here, or do you think there's smaller steps that we could take first?
Uh, so assuming unlimited resources, the bottleneck would be deprecation periods,
Yeah, makes total sense.
because currently the CAPI has infallible functions
Hmm.
that give you the internal representation, which means there needs to be the internal representation in the current form uh,
Ah,
for the current CAPI to work. That's not even taking into account this Unicode object, which people use directly.
mhm.
Right. So the problem we have is there is Unicode get data public CAPI function, which gives you the internal buffer and just gives it to you, and there's no way for it to fail.
Trying to find that now.
Unicode data. It doesn't even
Oh
have a
yeah.
get. Right. So you're supposed to call Unicode. What is it? Get Unicode kind, which gives you the kind,
Oh,
and then
yeah.
you call PyUnicode data, which gives you the data in that kind.
Yep.
And these are not documented to have any error cases.
Uh, but what and I guess the kinds are documented. So
Yes,
what
one
you end
byte,
up
2 byte,
with
and 4 byte.
is
Yes.
that people will build code around the assumption that there are three kinds, and then they will check for those three kinds, and they may not even have a case for it's not in those kinds
Yes.
because it's just written that way. And so to add a fourth kind, for example, for UTF-8 is a big problem.
Yes.
And so I think I've seen, I can't remember the full details of how this worked, but there was proposals to have the kind of other way around, right? Where the caller requests data in a specific kind,
Yes.
and
So
that would error if the data is not available in that kind, which doesn't necessarily mean that it couldn't be lazily decoded to that kind and a temporary buffer given, but
right.
it
So yeah. There is a better API that I have in my head.
mhm,
That is not the bottleneck. The bottleneck is getting rid of this API.
which would
Right?
take a long
Assuming
time.
assuming we can design, like we can always add stuff, right? We can design the best thing we can and add it to CPython. The problem, uh, which will determine how long a deprecation period we need, whether it'll be 2 years or 10 years or 20 years,
Yeah,
with that is the time scale we're dealing with, uh, is how fast can we deprecate these and how easy we can make the path for moving people away from these and the fallbacks, the behavior they'll get if they stay with these APIs, because people will stay with these APIs. There's a bunch of unmaintained C extensions that just need to continue working
yeah,
somehow, right?
absolutely.
So uh,
We're talking like
so
5, 10 years
we
at
have,
least, right? This is a complicated one, and it's so core to how everything works as well.
yes. On the other hand, the representation of Unicode strings has changed in the past. It is possible to do this. Uh,
Hmm.
Things have changed. It's harder to change stuff now after the 2 to 3 transition, of course.
Hmm.
And now we know that we can't just break stuff because people use it and they cannot update their code. Uh,
Yeah,
but it is possible. It is possible. It'll take decades, but it's possible. And the sooner we start, the sooner we'll get there.
okay.
Right. So yeah. So uh, that'll be the bottleneck. So to get to where we want to be, we need to design a good API,
Hmm.
implement that, then after that, start deprecating the old API, and then wait however long we need to wait, depending on the smoothness of the deprecation,
Yeah,
and then we get the benefits,
that makes sense to me.
or our children get the benefits, right?
Yeah. And then we can't even introduce, well, we couldn't introduce a UTF-8 path into this code in the until that uh, deprecation period is even complete, right? Like, because we would always need to have uh, the data and kind available until those APIs.
So
I mean, could you do
no,
something like uh, if the only available kinds are for backwards compatibility, you need those three kinds. Is
yes.
there a world, say, where a new API and implementation existed that could support UTF-8 interchange, and if a caller called one of those, say, future deprecated APIs, so Unicode kind or Unicode data, then a backwards compatible buffer could be internally allocated that otherwise is sitting around as null?
Mhm. Yes, we can definitely do that. The problem with that is allocation is fallible, and these APIs have no way to signal an error.
So you just have to abort, and then that's not great.
So you just have to abort. Well, on the other hand, on modern systems, allocations don't fail, right?
Because there's a lot of memory.
Most modern systems, the system will slow down to a crawl and halt
Fine, yeah.
before it reports an allocation error, which is of course configurable. But like, what do you do if you run out of memory?
I guess you have to be in a worst case scenario to have an extension using such deprecated API with a string large enough to cause a memory issue. Well, it doesn't have to, because it could just be a lot of data, I guess, in the system. It doesn't have to be a large string.
Right. And there's a compounding factor. Strings can be large.
Yeah.
Right? People load files into strings, right? Nowadays.
Yeah.
So
yes.
yeah, that's a bit of a problem. On the other hand, if you run out of memory, what do? You abort the process anyway, unless you're like a web server handling multiple tasks where you can easily kill one of the tasks. So as a person who take cares of the backwards compatibility and all these issues, I see this as a big problem, and I think we should do everything we can to make things good.
Okay.
On the other hand, people closer to the actual practice might see aborting as fine for old deprecated APIs.
Yes, but that's not a decision that we would be making today anyway.
Well,
that will need a lot of discussion from a lot of people before any kind of approach like that would be decided upon.
Right. Yes. So it's the only thing we can do, I think.
Is abort, you mean?
Yes.
Yeah.
So so we need some kind of deprecation period.
Yeah.
The deprecation period for API that everybody that works with strings is using. With my core dev hat on, the proper time for that is infinite. Like that's Python 4. That's not coming.
Yes.
That's like you switch to PyPy for that. You switch to another implementation. That's not CPython anymore.
Yeah.
Right. This API just needs to stay in.
Yes.
So making it abort, like deprecating it and making it abort a few years later, is the way to go. Like I think that's the only way we can proceed here.
Yes, but then still the answer is that the first step we should do is introduce new API, which is better as the first stage, long before we start experimenting with any of the other kind of formats.
Yeah, well, depending on how you think about your steps, right? So publicly, we need a good API. We need a PEP. We need a PEP that adds a new API.
Yeah.
And we need to explain why it is a better API.
Yeah.
Right? And then we need a PEP to get rid of the old API. And these can be the same PEP in case if our only reason for the future compatible API is so that we can deprecate the old one and get the benefits of that, they probably need to be the same PEP. Or not. I don't know. That's editing. Right, we get the future compatible API in. We might need to let it sit a bit. Then we deprecate the old API with some kind of off-ramp strategy for users. Then we wait for the length of the deprecation period, which is years or decades, depending on how much people want this and how much it breaks. And then remove the old API.
Yep.
And then we can switch the internal representation. I don't know if we can do it. So yeah, somewhere in step 3, we switch the internal representation, which means making the old API abort, presumably. No, not remove.
I'm trying to find a way to rephrase that.
Switch the internal representation, which means old API will will be less good. Yes.
Yeah, with some sort of hand wavy, and we could add new internal representation or optimizations, etc. at that time,
right,
if we wanted. And we don't have to, but yeah, there's presumably it's not like the moment we deprecate the existing string API, we can do step 3A anyway. We probably want to allow a couple of release cycles for that sort of thing to.
So there's one more step, and that is come up with a new internal representation.
Okay. Can we just?
Oh, we need to do that before I.
Yeah. I suppose it's worth doing that even before going down this whole road, right? Because you need to prove that there's something worthwhile at the end of the journey. Otherwise, why would you push the churn onto the ecosystem?
Right. Yes, and to prove that it's worth it, you probably need to implement all this and benchmark it, right?
Yeah.
And that's a lot of upfront work for something that might just get rejected.
Yeah, absolutely. So
we probably want to do something like a proof of concept where it just always aborts.
Yeah.
Then say, this could compute things lazily too, if but yeah.
Yeah.
Okay, so on the topic of a new Stra implementation, there's one more point probably want to keep in mind, which is Rust's internal, like Rust's string representation is not the only thing around.
Yes.
So the person who complained about my plan to remove the current by Unicode object structure was wrapping Java strings, and Java strings are the weird 2-byte like UCS2 UCS.
Is it UTF-16?
I think,
or is that?
Or
is that?
Or UTF-16, right?
I'm going to just put question mark. Copilot's claimed that it's probably right, but well, I don't know about an alternation.
Which are just weird, right? If it's ASCII, you just do a stride copy, and if it's UCS2, you need to see if there are any surrogates, and in the nice case, you just do a mem copy, which they want to be really well, or not even do a mem copy. What they would really like is to share the representation between Java and CPython in this case, and otherwise you copy. So
yeah, makes sense. You really want to be able to support multiple different formats like this and have the sort of performance characteristics that are desirable from each of them. So something that's truly flexible would be the goal.
Would it be?
Would be, I guess.
Because if you go for full flexibility, there's now a matrix, right? So I actually sketched out some of what the API could be for creating a Unicode subtype from data.
Yep.
I don't know how I can share it, so I'll probably just read it. So it needs there's a matrix of formats and flags, right? So the data can be in 4 different formats: UCS1 to 3, 1 to 4, and UTF-8. Right, that's like the internal representation. We probably don't want to do UTF-16 in CPython.
Yeah.
Doesn't really make sense nowadays. Yeah, in the future we might add new ones.
Yeah. Okay.
We want UTF-8. We're doing this for Rust, right? So if we don't want UTF-8, then it's useless to do this whole exercise.
Well, I mean, we say for Rust, but I think things like CPython
for
and
things like reading
WebAssembly
files
and the
nowadays,
browser, UTF-8 is a standard format. I mean, yes, you're right.
yeah,
Most files are very frequently UTF-8 encoded, right? So having UTF-8 encoded strings would be a massive efficiency for CPython as well.
right. And then come the flags. So there is a flag for
Yeah.
somehow consuming the buffer.
When you say consuming the buffer, you mean it owns the buffer?
So making like transferring ownership of the buffer to CPython, which means the buffer must be allocated with pymemmalloc, but basically you build the buffer first and then you give it to Python, so Python doesn't need to copy it.
Does it really need to be owned by pymemmalloc? Because you could presumably pass a pointer to a destructor if you wanted.
Or that, yes.
Yeah.
Yes. Right. Yes. Or pointer. The pointer, like the implementation complexity for destructor pointer is even bigger, so I just wanted that in the initial exploration.
Yeah. Okay.
Oh, a bit more complex. It will probably make sense for something like nmap a file and just give it to Python.
Yes, I think also
That would be nice.
for talking back about Rust strings, it's easier possibly to. I mean, Rust is working towards custom allocators and things like that, but typically at the moment the Rust allocator is not pymemmalloc. So it would be easier to say, hey, Rust allocated this, here's the pointer to how you deallocate this from Rust again.
Like, yeah, so the flag should be like, give the buffer to Python.
Yeah.
Might be a pointer or some other mechanism. Flag number 2 is, does this have a null terminator at the end?
Yeah, because you might have some buffers that do contain one and some that don't, and it would be nice if you didn't have to reallocate to add a null. But I guess is the problem that
all the old API needs a null terminator, and we need interrupt with that. So yeah, we need this. But if we're doing flags anyway, we need this.
Yeah.
And then the rest of the flags come in pairs, because there are 3 states. You can either know you have a property, or you know you don't have the property, or you don't know.
Okay.
And that would be embedded nulls. Is there an embedded null byte inside?
Okay.
Which probably doesn't really matter for Rust, but there's a lot of checking for this in CPython. And if we're kind of adding flags to strings, this should be one of them.
Yeah.
Right. So if we have that information, we need to keep it in the string. There's lots of bytes in there. Does the string contain lone surrogates? Which makes it invalid UTF-8, invalid Unicode. Not potentially.
Yeah.
We know or we don't know, or right.
Yeah.
Then, since we're talking about data that somebody passes in, I call this tight format. Is this like the tightest memory representation you can have for this string? Like, are you passing a UCS4 string with ASCII in it?
What would be the advantage of knowing that, other than knowing that you could reallocate it to make it more compact?
Well, if you're giving a UCS4 buffer to Python to make a string out of,
Yeah.
and you know that it needs to be UCS4, then Python doesn't need to check, and it's faster. If you're just giving me a UCS4 buffer and not saying this about that buffer, it might be ASCII, and Python needs to go through the string and check if it is ASCII and reallocate copy.
But that's only so that Python can end up with the most efficient memory usage for the string, right?
So the current representation is guaranteed to be the most efficient representation. So if we're
Okay.
converting to that, we need this.
And you don't think that that's something that can be reasonably relaxed?
No, I don't think so.
Because it's guaranteed that CPython will be as efficient as possible? Is it because consumers require? I think I don't
It's
see.
currently guaranteed. We also have a fast is this ASCII function, which this is a subset of, or superset of.
Oh, I see. Because there is ASCII checks for the kind or similar.
Well, okay. There's a bit more complexity. There's actually a yeah. Maybe let's keep this in a brainstorming stage and look for reasons why you need this later. That's a bit of a rabbit hole here.
Yes, that's
So
that's
as brainstorming bullet point, this should be fine. Okay, let's
yeah.
leave it at that for now. Next up, is this valid UTF-8 or valid Unicode? Does this have invalid UTF-8 sequences like overlong encodings? Does it have an out-of-range value in the UTF-8 representation? Is this valid valid encoding? Valid, not necessarily UTF-8.
Yeah.
Is this valid Unicode? Basically.
Yes. Okay.
So slash encoding.
Mm-hmm.
Right. So you could split this into invalid Unicode sequences like overlongs, out of range values for Unicode, and lone surrogates, which I think need their own flag.
Yes, you already mentioned lone surrogates before.
Yeah, and like overlong UTF-8 sequences and out of range values. And so the first one should be overlong UTF-8.
Okay.
Yeah. And that's the ones I could come up with thinking about CPython's, Java's, and Rust's use cases. So how many bits are we looking at? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
For the flags.
For the flags, which is fine.
Yeah. And I guess if you put lone surrogates into this just general valid Unicode encoding flag, then you can get away with 8. But presumably you had a good reason for having lone surrogates out.
Yeah, the like decoding from UTF-816.
It's easier.
Yeah, you want to have this separately.
Okay. All right. So
So these were flags for a function to create a Python string from a data in any format.
we're talking about a hypothetical. I
So the
guess it
function
would
would be
be,
named Unicode subtype from data.
and the reason for subtype from data is because you were allowing for.
Yeah, you also pass in the type of the Python, like Python type of the resulting object. It takes a class. It takes the data, the size or number of bytes, and the input buffer, the format, and the flags.
Yeah. And I guess this might really be some enum. I've written slightly backwards syntax because I've started writing Rust. Something like this.
Yeah. Unicode format enum with UTF-8 added.
But I guess you want that to not be closed for the future. It's
Oh,
just
Unicode format is not a thing now, so
yeah,
I'm adding
yeah,
that.
yes,
Right.
hypothetical.
Yeah.
And so the idea is that this function then would be able to just build
Oh,
a.
one more thing. One more thing. This needs to. So if we have the flag telling Python to take ownership of the object,
Mhm.
I guess if we're passing, so what
Uh,
happens if the buffer is in an incompatible format? So Python needs to copy it. I guess
uh,
it should call the destructor immediately, right? If
so
you
you
pass in
might
the
need a destructor,
yeah.
which uh,
The
something
destructor
like
might be part of the type.
uh, maybe. I guess. And if we go for the initial constraint that it's
If we go
pymem
for
malloc, we
that,
don't need that, right? Anyway,
if what?
if
If
the
we so yeah, so if we go for the malloc buffer, then this function needs to return three states, either error or success with the buffer taken, or the case where it doesn't take ownership of the buffer, unless it calls the destructor itself. Do we want that to call a destructor if it didn't take ownership of the buffer?
I would well, thinking with my Rust hat on, I typically, if you write a function that takes ownership of something, then it's also responsible for freeing it on error pathways or whatever. And then you as a
Sure.
caller don't need to check. I guess that you lose the opportunity for, oh, PyUnicode didn't actually take hold of this buffer, so
Oh,
now I
so
still
okay.
have the buffer. But what do you practically
I know
gain?
how I added up here. So one thing here is that these flags should be extensible. So in the future, we might need to add a new one,
Yeah,
right? If we were adding this take ownership flag right now,
yeah,
we need the caller to be compatible with old version of PyUnicode subtype from data, which doesn't know about this flag. So we either add something to let the new callers query if the function knows about this flag or not, or we make the by Unicode subtype from data return information about whether it took ownership or not.
And you'll say if we add the buffer ownership transfer flag later.
Yes,
Um,
because all the flags are designed so that if there's 0, you can ignore them.
would it make sense to have, if you wanted to go that route, would it be simpler to add a second API in the function in the future, which would be say PyUnicode subtype from owned data or something like that, where you then have to not yeah, I guess you widen your API rather than adding a new flag, but
Yes.
at least you could have a different shape of that function that
So widening the API is definitely possible. The problem with that is you set a minimum version of Python that the caller will be compatible with, which means users of the stable API can start calling this after like 5 years, but not immediately.
uh sure. Um Whereas if you change just the API or just the flags, then what you're saying is that say you're building for the stable API Python 3.12 or whatever, or well, whichever one has this API in it, then if at runtime you detect you're on a newer version of the interpreter which can support owned buffers, you could do it. You could do it. You could upgrade at runtime, you mean, to transfer the buffer in.
Well, well, you could upgrade at runtime, which means you cannot link to the function in the normal way you need to, like.
Oh, I don't mean call a different API or different symbol. I mean, so you're saying make the flag.
Yeah, I see. Ask Python what it supports, right? Which we probably want anyway, because we want to ask for what the preferred format is. Like if you have
Oh, I
if
see.
you're creating the buffer in the first place, and UTF-8 is just as easy to create for you as UCS2, you can ask Python which one it wants.
Hmm.
So yeah, we could add it there. Another thing we could be returning from this is the set of flags that is true about the string, which also should probably be its own function. Like if Python
Yeah,
determines that this encoding is the right one for it, and then it could somehow return the flags. I don't know. Well, this is a good
yeah. This is a good first step anyway. We can.
step. Yeah,
Okay, we're nearly at time for what I had for today. So I guess what
and
we
didn't get
can.
to write any code at all.
That's always the way, though. When we first think about a problem, you always need to understand the problem before you can start writing code. So that's not a huge worry.
Is
Um,
this the road uh, we're embarking on for the
uh,
next 20 years?
I I mean, it feels like to me making it possible for CPython to support UTF-8 format, as you've pointed out, like there's lots of existing UTF-8 text out there, which CPython currently pays a decoding cost on, which includes Rust strings, but so it's not actually a problem just specific to Rust, even though I obviously have noticed this. And so feeling a way forward is interesting because it can help solve this problem for lots of callers.
Yeah. I mean,
Um,
it would be great if you could just mmap a file and make a Python string out of that. Done.
yeah, I can see that being incredibly
But
powerful. Um, and then in that case, talking about all these flags or whatever, that's like a non-owned buffer because it's M mapped, and you can say the format is UTF-8, probably not null terminated again because you're M
the
mapping it, and
yeah, The problem with that is you index in the middle of that buffer, and now you allocate a UCS4 buffer for it.
Yes,
Yeah.
so you end up paying the same cost anyway. Uh,
Anyway, and this can raise an error.
yeah, so it makes other operations not so good. So it's not obviously better. So
I mean, it it is better. It is obviously better. There's a huge use case for loading a file and just pushing it somewhere else.
yeah,
Indexing, uh, I mean, it's probably fine to say indexing is less performant now, or even to say, hello, Mark Shannon, could you give us a good data structure for building an index?
yeah. And ideally one that can be built lazily. I don't know whether that's even plausible. I have no idea.
Yes, it is. The whole thing is supposed to be lazy.
Yes. I guess I meant like if you index to character 5, you don't need to resolve what the indexes are for characters 6 to whatever your end of a string is. I don't know whether that's
Yes, and the same thing from the end, and
yeah, yeah,
optimization lovers heaven.
yeah. Okay. My feeling is that what would be really cool to do is to at least on a prototype start playing around with more seriously what does a UTF-8 format look like in CPython and kind of feel our way through this API at the same time, the forwards compatible one, knowing full well that we probably won't get everything. Well, we probably don't want to go for like a super well optimized UTF-8 and all of these things. Like, as you say, we could put a lot of work into this to find that there's reasons why it's very challenging or just not going to ever make it. So we don't want to like hyper optimize or do any of that kind of stuff. But beginning to play around with it and see how we make it work would be interesting because I'm imagining is the second we add a UTF-8 format to Python strings, then everything starts not working, and so we very quickly feel about what needs to be made compatible in CPython for such a thing to even function, right?
Right.
And that will tell us the
Okay. Yeah.
APIs that we need.
Sounds good. Okay, so we go for a proof of concept that just aborts on errors if we can handle them properly, and just add a new kind.
Yeah, something crude like that, I guess.
Okay,
Um,
that sounds pretty good.
it would at least teach us about, I think, what some of the hard points were. It would be quite fun to build it, and then hopefully it tells us what we want this API to look like at the same time. Like we could presumably design it so that the only way we can build a UTF-8 buffer would be from this API,
Oh, well,
or
I
something.
kind of want to add this API anyway to
Yeah,
start deprecating the internal structure.
I mean, that's the
Uh,
other thing. That's probably what Python 3.16 now is a likely target for this API.
oh, definitely.
Hmm.
That's the earliest it can get in. This is way too complicated. So if it needs to be a PEP, like the steering council
Yeah.
is, I think, at capacity for the beta period cutoff.
So perhaps we can do both at the same time, right? We could implement this API, have lots of cases that are currently unsupported and fail or whatever, but we
Now,
could
the
make,
problem with this API is it's big and complex, so it needs a motivating use case. And I'm not sure I really have something that motivates such a big change.
yes, I guess what I
So
was going to say is
proof of
this,
concept is probably better.
well, but what if with the proof of concept, we'll need a way to construct a Unicode with a UTF-8 buffer, right? And so we could have something that's approximately this API, maybe not the full API itself, and we could have lots of cases that don't work initially.
Now we have PyUnicode from string and size.
Uh, which
If
is
it's just UTF-8
which is
buffer.
of course a UTF-8 buffer right back where we started. So we can make that just, and that
Yes,
has none of the ownership transfer or any of those kinds of interesting features, but it gives us a way to skip decoding and just populate a UTF-8 buffer. So that
right.
doesn't become a motivating use case for this API. Oh, no,
Yes.
yes, it does, because we need something like this API to make eventually the internal changes we need
Right,
if the motivating use case of UTF-8 buffers actually yields a promising result, right?
right. Well, yes. I mean, you need this API to get motivation for each individual flag. Or do we
Yes.
need to track embedded nulls? Probably makes makes the benchmarks this much faster.
Yes. So, and by that you mean that some functions can fast path and some can't, or you wouldn't be part. It wouldn't be safe to
So
even
internally
expose
in
that.
CPython, there's a bunch of checks for embedded nulls,
Hmm.
which are linear.
And
So
so
if
if
we
you know
store the
that,
flag whenever we know, uh, things will probably become faster.
and I guess
And that's the kind of
similarly,
thing you need to change the structure for. And I
yes,
could probably do it today, but
you have to change that bit field, which is possible, but
no,
it's not.
you can add a bit to the end, but it's kind of
Yeah.
tricky.
Hmm. And Unicode kind would have to become larger anyway, or well,
Not the kind, just add a flag.
yeah.
What format does the flag come in?
Hmm.
Do we let users say upfront, assume that this doesn't have embedded nulls in it?
Yeah. Okay, cool. I think let's end the stream here. You
All
and I
right.
can continue to catch up just for a second after. Thank you everybody for joining us today, and sorry again for the kind of the technical slow start. But
It'll be better next time.
yeah, I hope you've all enjoyed our discussion about Unicode objects and what we could play with in the future. The next stream, I can't remember the exact date, but it's going to be on a Friday, same time slot, towards the end of April, start of May. I think it might be off my head. I think it's 1st of May, but that could be wrong. I don't know if that's even a Friday, but that's just a date that sticks in my head for some reason.
That's
Um, so we will look forward to seeing you there, and we will probably start playing around with prototyping this implementation at that time. So take care, everybody, and have a great day.